Assalamualaikum and good morning, everyone. Okay, so before we start our class, I want to remind you on assignment number 3. So the due date is this Sunday, okay, before midnight. So assignment number 3 basically just follow the steps given in the documents. Okay, so today we are going to learn about electrical stimulation model. Okay, so lecture number 4 is about electrical stimulation model. So at the end of this course, at the end of this lecture, you will be able to understand the application of electromagnetism model in modeling a biomechanics system, and solve and analyze various electromagnetism model of biomechanics using COMSOL multiphysics. Okay, so before we can go into understanding about electrical stimulation, let's go back to some basics about the electromagnetism in general. So matters composed of atoms consist of positive charged nucleus and also negatively charged electrons. So because of these particles, positive and negative charged nucleus and electrons, so it creates magnetic fields in between various atoms in a matter or in a material. So to describe this electromagnetic fields, Maxwell, this person, if he's still alive, you guys can find him and do something to him lah. So he created this Maxwell's equations. So there are 4 equations that relates electric field E. So E is electric field and B is the magnetic field. So if you still remember SPM electromagnetic topic, you have learned about right hand rules, Fleming rules. So all of these are basically came from Maxwell equations. Okay. So all of the rules, right hand rules, Fleming rules, all of them are coming from this Maxwell equation. So the most important things are the E is the electric field, and B is the magnetic field. So usually we will analyze electromagnetic equation in static cases. We can also analyze in dynamic case, but for static case, we assume that the charge and currents are constant. It doesn't change with time. So all of the time derivative equation or time derivative terms in this equation can be assumed equals 0. So for static case, the electrostatic equation is given by the first 2 equations, and the magnetostatic is given by the second 2 equations. So it's similar, but without the over time derivative. Okay, so in this equation, we need to define in COMSOL multiphysics or in any finite element software, we need to give the material properties of a material or something that relates to the electromagnetic. So the properties are this rho here and also this epsilon naught and c squared. Okay, so we will look more on this rho and epsilon naught. What are they? So firstly, the electric field. The governing equation for electric field E under electrostatic conditions as given previously. So this is the electric field equation. So the electric field E can be related to V. So V is the electric potential, or in layman term, is the voltage. Okay, it's the voltage difference that when you do circuit analysis, you measure using multimeter. So electric field V or electric potential V is related to E by this uh, curl, okay? Not curl, divergence or del of V. And then the other equation for electrostatic, del dot E, del dot electric field equals rho over epsilon naught. So rho here represent the resistivity or the resistivity of a material towards electrical propagation. So resistivity, you can treat it as how well a material can stop a flow of current, the flow of current. So if you have metal, then the resistivity will be very low because metal can conduct electricity. But for wood, for example, or rocks, the resistivity will be very high because it resists the flow of current. So the conductivity, meanwhile, is the inverse of resistivity. So conductivity, sigma equals 1 over rho. So conductivity is the reverse meaning of resistivity. So conductivity is the ability of a material to conduct electrical current. So metal, the conductivity will be very high, but for rock, the conductivity will be very low. So rho, if you still remember circuit analysis, it is measured using unit ohm. But for conductivity, the unit is Siemens S. Okay. Conductivity can be related to electric field E with the electric current density. So J is current, something like I equals V over R. But in this case, J is current density, okay? Ketumpatan current, ketumpatan arus equals negative conductivity times E. So in this lecture, the important material properties that relates material conductivity of electrical current is this sigma or rho. Okay, sigma and rho is one of the properties that you need to know to simulate electrical stimulation in your final element software. Okay, so let's look at an example of how we can use electrical stimulation model or electromagnetism model to understand something related to biomechanics. So one of the common things or common application of electromagnetism is to study how an external defibrillator works. So defibrillator is a device that used to when your heart is suddenly stopped or not working properly. So your heart produce electrical current. If you know, so the heart produce electrical current that causes the heart to contract. Okay, so when your heart doesn't produce enough current, so your heart cannot contract properly. So it still contract, but maybe the pumping ability is not as similar to a normal person. So sometimes if you watch TV drama, sometimes the patient suddenly showing a sign of the heart stopping. So the doctor will use defibrillator it will apply, he or she will apply a current to the chest. So this current will go to the heart and um, supply an external current so that the heart can pump back the blood through the whole body. So in this example, we are using defibrillator. So AED is similar to defibrillator, but it is external, meaning that it is available not in a hospital, maybe available in shopping malls or in office, for example. And it's a portable electronic device that automatically diagnose the life-threatening cardiac arrhythmia. So cardiac arrhythmia is when your heart doesn't produce um, a normal electrical signals in the heart. So maybe the heart still produce electrical signals, but not periodic. Maybe sekejap satu saat dia ada electrical signal. Maybe the next cycle selepas 3 saat. Macam not regularly, okay? Maybe the pulse or the electrical signal produced is not regular. And also we have pulseless ventricular tachycardia. So it's something similar to arrhythmia related to irregular rhythm of electrical signals in the heart. So if you have AED, it can able to treat through defibrillation. So defibrillation is the application of electricity which can stop the arrhythmia and allows the heart to establish back the electrical signals following a normal rhythm in the body. So to model AED, maybe we can look at a simple case study. So consider the following idealized, okay, very idealized geometry of electrode placement for an AED. So we can assume our body or abdomen as a square, as a cuboid, kotak, okay, a box. So we can assume our body as a box, and then we draw an electrode on one surface. So the first surface here is the top electrode, and then we draw another square on the surface to represent another electrode. So we can supply a current to one electrode, and then we can make the other electrode as a ground. So we hope that the current will flow from the top electrode flowing to the grounded electrode. So what we can do here is that we want to see how much current actually flowing inside the abdomen or inside the body, and we can analyze a lot of things from here. But this is ideal geometry, meaning that it's not really a human geometry, but it's a representation of a human geometry, a simplified geometry, I would say. So here, what we want to study is what is the voltage difference between the electrode pedals when you apply a DC current of 10 ampere at the top electrode. Okay, so after we simulate, we can get something like this, the results. So obviously at the top electrode, the voltage is higher compared to the bottom electrode because it is grounded. But you can see that there's a changes of voltage. Okay, maybe the current is flowing from the top to the bottom. Okay, so this is the modeling step. If you have console, we can do this together. So let's do this using console. Okay, so since our geometry is a cuboid, so it's a 3D, okay? A 3D simulation. So last week, we have seen a 2D axisymmetric simulation. So What is axisymmetry? Basically, it's a rotation about the central axis. So now it's a square, I mean, it's a cuboid. So you can use 3D simulations. Okay, so we start with by choosing model wizard and choose 3D. And then we want to find the physics for electromagnetism. So here in COMSOL, we use AC/DC. Okay, AC/DC. So it's in here, AC/DC. If you drop down, you can choose this electrical currents EC, or you can just type in the search electrical currents. Then you will find a similar physics. So just double click and then click study. So we want to study the static case. Okay, a static case. Sometimes we can study time dependent, but in this case, we study for stationary static case. So just click stationary and then click done. Okay, so we start by drawing the geometry. Okay, so we start by drawing the geometry. So we can start by drawing the cuboid. So we can go here to the geometry and choose block. Okay, we start by drawing a block. So you can choose it here, or you can just right click on geometry, right click geometry and choose block. Okay, there are two ways you can draw a block. And then in this block, so you just need to specify the size and shape. Okay, so in this case, the X and the size of the cuboid, the X 0.3, so the width, and then the Y and the H, the height. And then start at corner. So this is the corner at position 0. And after that, you can just build selected. So you get a cuboid here. Okay, now we want to draw these electrodes. Okay, so we have two electrodes in the cuboid. So we want to draw one here and another one down here. So to draw that, we can just draw a square on the surface. So to draw a square on the surface, we can choose this plane here, the forward surface here, and then just draw a square on that surface. So what the next step do is basically drawing, choosing a plane, choosing which plane you want to draw a square. Okay, so just go to geometry, right click and select work plane. So we want to work on the frontal plane here. So the front plane is located on a Z and X axis. Okay, Z and X axis. So we select Z X axis. Okay, so the indicator is shown here. So when you choose Z X axis, so you get this macam kertas graph, okay, a graph paper showing on which plane you are going to draw the square. So let's say if you choose XY, so it is down here. You want to draw a square down here. But no, you don't want to draw here. You want to draw on the frontal plane here. So we choose ZX. Okay, so we want to draw an electrode here. So click bit selected and then go to plane geometry here. So now we can draw a square. So right click and choose square. So again, the side length is 0.1 based on the figure given. But now you need to position this square. So this square now is in horizontal, okay, horizontally. So if you look at the first figure here, so it is shown like this kertas graph. But if you draw a square, this square, and go back to this plane, the square is actually here. So dia you kena positionkan balik lah. So you need to bring it up and make it somewhere about center, okay? Okay, so here for the square we need to bring it up and make it a bit center, okay? Bring to the right and then bring up. So the instruction is already given, so you just write the position, okay? And bit selected, corner at 0.2. What happened? Okay, so instruction is salah. So 0.25. And then we need to check again. And then we need to bring about 10 cm. So 10 cm. No. Salah. Okay. So it's measured at corner. So this corner, so you need to bring it up 0.05. Okay, sini betul lah. Kita yang salah baca, sorry. Okay, so after you draw, then you get the right position, okay. And then we repeat the process to draw another electrode on this side, okay. So similarly, right click, choose work plane, and then choose a plane on this side here. So you can check by click bit selected whether you have chosen the right plane. But in this case, the tutorial is already give you the plane that you have to draw. So YZ and then the location of X is 0.3. But later maybe if in Pascal, if the figure is slightly different, you can just play around with this number, okay? Okay, so we want to draw an electron on this plane. So this is our plane, and then we choose a square, and then we change the width. So it is here, and then we need to bring it up a bit by changing the Y. So the XW here represent this distance, the X direction here, and then YW represent the Y direction of this graph paper. Okay, now we have our electrode drawn on the abdomen. Then we can go to setting the electric current. So as I said, for electromagnetism, we only have one material properties to set, which is the conductivity. So if you go to current conservation and choose this electrical conductivity, and just define your own user-defined conductivity. So in this case, it's equal 1. Okay, so the whole abdomen has conductivity equals 1. So you can also use definition from materials. Okay, so if you choose from materials, then you need to choose what material you want. Okay? You need to browse from library. So this is depends on what materials are given, but it's easier, always easy if you can just put the numbers here. Okay, so you don't need to uh, trouble yourself to find what materials from libraries. Okay, so we set the electrical conductivity. Then we need to set the boundary conditions. So the first boundary condition is we need to apply the voltage or current on the top electrode. So to apply that, we use this second boundary, boundary 6. We apply normal current density. So normal current density, so right click electrical current and choose this normal current density. And then choose this top electrode. So it's boundary 6. Written here, boundary number 6. And then we just write the electrical current density. So now the top electrode has a current entering the abdomen. And now we need to set the bottom electrode as a ground. So right click again, choose ground, and just choose the bottom electrode. And then we can check the boundaries 1, 2, 5, and 7, whether it has been set for insulation or not. So insulation is by default given to you. So if you look at the insulation section here, you will see that boundary 6 and boundary 8, there's a word overridden written on it. So overridden meaning that this two boundary will not be applied for insulation, but instead it is applied with, for example, boundary 6 with normal current, and boundary 8 is grounded. Okay, so the other boundaries are insulated. Okay, insulation means the current cannot go out from the abdomen. It will only flowing inside the abdomen. Okay? So the other surface are insulated. Now we have set everything for the physics and boundary conditions. Then we can try run the simulation. Okay, so the mesh will be automatically. It will automatically mesh. So we can just try compute. Okay, it's quite fast. And then we can plot these results here. So the result given to you is by default. So you can just turn off, okay, disable, okay, tak nak result tu. So you can right click result, choose 3D plot. So in the slide, it plots for the voltage, okay, electrical field, electric potential. So here in 3D plot group, you just choose volume. And by default, it already gives you the electric potential. So you just click plot. Okay, so you get the electric potential in the abdomen. So you can play around with more of variable to plot by clicking this, okay, or this, okay, either one. So if you choose this, then you can go to this electrical current, and there are so many things you can plot. You can plot displacement of current, electric potential, energy, global, whatever, heating losses, and material properties. Okay, but in this case, we are interested to plot the electric potential. Okay, and you can also change the color. Okay, so this is uniform color or rainbow color, heat cam light. Okay, but normally people will use rainbow color. Okay, and then you can either want to choose legend or reverse the color table. There are so many functionality that you can explore. Okay, now we have plot the electric potential. So what else we can do with this? So in this tutorial, in this example, we are interested to determine the impedance. So impedance is basically the resistance inside the abdomen. So transthoracic impedance. So impedance is resistance. So transthoracic impedance is basically the impedance inside your the location where your heart is located. So your heart is located inside your rib cage ataupun tulang rusuk rib cage. So the rib cage consists of inside the rib cage you have lungs or the thoracic. So thoracic, lung, trachea, saluran pernafasan. Okay, tak tahu lungs apa. So lungs is paru-paru and trachea is your saluran pernafasan. So transthoracic means that the area in between the your rib cage. Okay, so the resistance to the flow of electricity through the heart muscle during defibrillation. So the resistance for the defibrillation current to flow to the heart is the thoracic structure. Okay, so due to the lungs, the trachea, the rib cage, it causes resistance to the flow of current from defibrillator to the heart. Okay, macam penghalang, okay, like something that prevent the current to flow fully to the heart. Okay, so this structure produce resistance to the current flow. So inside this structure, there are a lot of things like skin. Our skin also produce resistance. Subcutaneous tissue. Subcutaneous tissue is your soft tissue surrounding the rib cage, like muscle, lemak, for example, your fats. Okay, and then you have rib cage and sternum, and the lungs and the pericardium. Pericardium is a layer of a very thin layer that covers the heart. Okay, so it's a pericardium. So for detail, Google, okay, Wikipedia. I don't remember all of these. Okay, just some basic knowledge. Okay, dah tua dah lupa. Okay, so the best way to reduce the impedance. So there are impedance already exist in your body. So you cannot do anything. You cannot remove your lung or rib cage just to apply current to the heart. Okay, so if you remove all of this, mati terus. Okay, so you cannot do that. So you can only reduce this impedance and thus deliver maximum current or optimum current to the heart. So to do this, we doctors usually apply some gel, okay, gel or gel pads. So the pads, doctor usually put a gel. So this gel is something like reduce this impedance. Okay, so usually when you want to do some electrical experiment on patients, like ECG, electrocardiogram, or EEG, electroencephalogram, yang letak kat kepala tu. So the experimenter or researcher will put gel on the electrode before putting it on your head or on your chest. Okay, this gel will reduce resistance, okay, and optimize the electrical current flowing into the body. So usually the transthoracic impedance is about 70 to 80 ohms. Okay, so impedance, as I said earlier, it's resistance. So the unit is ohms. So to calculate the impedance in this example, we use this formula: impedance Z equals V, the electrical potential, divided by electrical current. So V is the V active electrode is the average voltage on the electrode and on the active electrode with an area A. So V equals the integration of V dA over A. Astaghfirullahaladzim, apa ni? So we need to do some integration. And not manually, we can use software. Kalau manual, sampai esok tak siap. Okay, so let's do this settings to calculate the transthoracic impedance. So go back to our simulation results. So before we compute the simulation, we can go back as one step prior. So we go to component, right click, in definition, right click and choose component coupling, integration, okay. So this instruction given in slide is using earlier version of console. So the newer version, it's inside this components coupling, integration. So choose integration. So the software will automatically integrate for you. You don't have to integrate by yourself. So we choose integration. So we want to integrate the voltage on the active electrode. So active electrode is the electrode number 6 or the top electrode. So by default, if you choose integration, the geometric entity level here is by default domain. Okay, so domain represent the 3D geometry. So you need to choose the boundary, okay, the boundary or the top electrode. So change here to boundary. So now your mouse will only choose the surface or the boundary. So if you choose edge, for example, you will choose only lines, okay, like this line, line here, here. So if you choose points, so you will choose only points. Okay, dia akan highlight point je. Masuk sikit lah sebab point kecil. So make sure you know what you are integrating. So in this case, we are integrating the electrodes. Okay, so we integrate the potential inside electrodes. So we choose boundary. So we choose the top boundary. So there are other settings here. At the moment, tak payah tukar. Okay, benda ni orang advance akan faham. Okay, there are so many things. So for now, just integrate over this surface or the top electrode. And then we need to define a variable. So right click definition, define a variable. So we want to integrate the potential inside the electrode. So maybe we name it the integration of V. Integration of electric potential inside the electrode. So what we can do now is that if you look at this integration, so in this integration, the name here, integration 1, bracket INTOP1. So INTOP1 meaning integration operator number 1. So console created for you an operator or a calculator to allows you to integrate. Okay, so now you can just use this calculator to integrate any variable that you want, but the integration occurs only in the electrodes. So you write INTV, so you want to integrate inside the electrode only the electric potential. So you just write INT operator 1 bracket, and what you want to integrate. So you want to integrate the voltage, okay, or the electric potential. Okay, so check the unit. So integration of potential about an area will have unit voltage meter squared. Okay, so this is correct. Okay, so this expression means integrate inside this electrode the electric potential. It integrate the electric potential. And then you want to find the area of this electrode. So area or A. So to find the area, so you just integrate inside the electrode, integrate the value 1. So when you integrate value 1, you get the area, okay? So yang ni mathematics, okay? Tak tahu macam mana explain. Maybe tak belajar kot, tapi integrate one, you get the area. Okay, so always integrate one, you get the area. If you integrate over the domain, you integrate one, you get the volume. Okay, but for now, to make your life easy, integrate one over this area, you get the area of this electrode. Okay, and then lastly, we want to determine the voltage average. So V average equals INTV over area. So you get the voltage, the unit. And then to find the impedance, so impedance Z equals V average over 10. Okay, so now Z is a reserved name. So earlier version of console, Z is not a reserved name. So now we cannot use Z. So we need to use something else. Maybe Z average lah, apa-apa lah. So Z average, you get V over 10. So 10, we need to put a unit. Okay, so the unit is ampere. So you get ohm. Unit ohm. Okay, so this is only variable. So it doesn't calculate yet until you compute the simulation again. So you need to compute again. So after you compute it, you can view the results of this ZAVG. So to view the results, you can go here. Derive value kot. Sini boleh kot. Volume. So just write ZAVG. If you plot. So the ZAVG will be 10.36. Okay, this is one way to determine the value of ZAVG. The other way is you can use derive value here. And maybe choose average. Global evaluation. And inside here, just write ZAVG and evaluate. So you get this result here, 10.36. Okay, so there are so many ways you can get ZAVG. Okay, so I hope you can explore. Okay. So here, more explanation. INTOP one means integration operation that you define. Okay, so that's it for today's class. So try the tutorial, and I hope you can explore on the plot, on the derived values, because in your test, you will be tested on how to plot something, how to calculate something. Okay? And after you go through the tutorial, you can try assignment number 4. Assignment number 4 is basically, I think this is last semester punya test number 2. So you can get an overview about how the test looks like. Okay, so try explore, and we will discuss test 2 this question after you submit next week. Okay, any question before we end this lecture?
No, sir.
No, sir.
Okay, hi, tiba. Okay, so please do your assignment number 3. Familiarize yourself with COMSOL and submit before Sunday midnight. And for assignment number 4, try explore. Okay, explore your COMSOL. And tomorrow, no class. Thank you very much, and see you next week. Inshallah. Assalamualaikum. Bye-bye.
Bye bye.
Thank you, sir.
Thank you, sir.